The unit circle is a circle centered at the origin with a radius of 1. At 0 radians, or 0 degrees, the corresponding point on the unit circle is 1, 0. Now, let's consider pi over 6 radians, which is equivalent to 30 degrees. To determine the coordinates of the point on the circle, we analyze the right triangle formed by this angle. This is a 30, 60, 90 degree triangle, which has a well-known relationship among its sides. If the hypotenuse is 2a, then the shorter leg, which is opposite 30 degrees, is half of the hypotenuse, or just a. And the longer leg, which is opposite 60 degrees, is the shorter leg multiplied by the square root of 3, or a times the square root of 3. Since you're working with a unit circle, the radius, which is also the hypotenuse, is 1. So we find that the shorter leg is 1/2, and the longer leg is the square root of 3 over 2. Thus, the coordinates of the point at pi over 6 radians are the square root of 3 over 2 and 1/2. Notice that these coordinates represent the cosine and sine of the angle. This means that the cosine of pi over 6 is the square root of 3 over 2, and the sine of pi over 6 is 1/2. This illustrates how the unit circle provides the values of cosine and sine as the x and y coordinates of a point at a given angle. Now let's consider pi over 4 radians, or 45 degrees. The right triangle formed by this angle is a 45, 45, 90 triangle, where both legs are equal, and the hypotenuse is a leg times the square root of 2. Since the unit circle has a radius of 1, the hypotenuse of this triangle is 1. To find the length of each leg, we divide the hypotenuse by the square root of 2, giving 1 over the square root of 2. Rationalizing the denominator, we get the square root of 2 over 2. Thus, the coordinates of the point at pi over 4 radians are the square root of 2 over 2 for both x and y. This shows that the cosine and sine of pi over 4 are equal. Now let's consider pi over 3 radians, or 60 degrees. Placing the corresponding 30, 60, 90 triangle in the unit circle, we use the hypotenuse of 1 to determine the side length. The shorter leg is 1/2, and the longer leg is the shorter leg times square root of 3, resulting in the square root of 3 over 2. Therefore, the coordinates of the point at pi over 3 radians are 1/2 for the x-coordinate and the square root of 3 over 2 for the y-coordinate. At pi over 2 radians, or 90 degrees, the terminal side of the angle lies directly on the positive y-axis. Unlike the previous cases, no right triangle is formed because the point is exactly on the unit circle's vertical axis. Since the radius of the unit circle is 1, the point at this angle is at the top of the circle with coordinates 0, 1. This means that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. Now let's consider 2 pi over 3 radians. The reference angle is pi over 3, meaning the triangle formed is the same as for pi over 3 radians in the first quadrant, but now the terminal side is in the second quadrant. The hypotenuse remains 1, and the side lengths are unchanged. However, the x-coordinate is negative because it extends left of the origin, while the y-coordinate remains positive. This gives coordinates of negative 1/2 for the x value and the square root of 3 over 2 for the y value. Therefore, the cosine of 2 pi over 3 is negative 1/2, and the sine is the square root of 3 over 2. At 3 pi over 4 radians, the reference angle is pi over 4. The side length remains the same as for pi over 4 radians, but the x-coordinate is negative due to its position to the left of the y-axis. This results in coordinates of negative square root of 2 over 2 and square root of 2 over 2. At 5 pi over 6 radians, the reference angle is pi over 6. The triangle is positioned in the second quadrant, making the x-coordinate negative while the y-coordinate remains positive. This results in coordinates of negative square root of 3 over 2 and 1/2. At pi radians, the terminal side lies on the negative x-axis, meaning no reference triangle is formed. The point on the unit circle is directly at negative 1, 0. This gives a cosine value of negative 1 and a sine value of 0. At 7 pi over 6 radians, the reference angle is pi over 6. The triangle is positioned in the third quadrant. The x and y coordinates take the same values as in the first quadrant, but are both negative. This results in coordinates of negative square root of 3 over 2 and negative 1/2. At 5 pi over 4 radians, the reference angle is pi over 4, and the triangle is in the third quadrant. Both x and y coordinates are negative, giving coordinates of negative square root of 2 over 2 and negative square root of 2 over 2. At 4 pi over 3 radians, the reference angle is pi over 3. The triangle is in the third quadrant. Both coordinates are negative, resulting in negative 1/2 for the x value and negative square root of 3 over 2 for the y value. At 3 pi over 2 radians, the terminal side lies along the negative y-axis, meaning no reference triangle is formed. The point on the unit circle is directly at 0, -1, giving a cosine value of 0 and a sine value of -1. At 5 pi over 3 radians, the reference angle is pi over 3, and the triangle is in the fourth quadrant. The x-coordinate remains positive, while the y-coordinate is negative, resulting in coordinates of 1/2 and -√3 over 2. At 7 pi over 4 radians, the reference angle is pi over 4, and the triangle is in the fourth quadrant. The x-coordinate remains positive, while the y-coordinate is negative, giving coordinates of √2 over 2 and -√2 over 2. At 11 pi over 6 radians, the reference angle is pi over 6, and the triangle is in the fourth quadrant. The x-coordinate remains positive, while the y-coordinate is negative, resulting in coordinates of √3 over 2 and -1/2. These are some of the most common radian measures along with their corresponding cosine and sine values on the unit circle. Understanding these values helps in solving trigonometric equations, analyzing periodic functions, and recognizing patterns in the unit circle. Since every point on the unit circle satisfies the equation x² + y² = 1, substituting cosine theta for x and sine theta for y, we get cosine squared theta plus sine squared theta = 1. This equation, known as the Pythagorean identity, holds for all angles. It comes directly from the Pythagorean theorem applied to the right triangle formed inside the unit circle, where the hypotenuse is always 1, the adjacent side is cosine theta, and the opposite side is sine theta.